In this video, we'll be continuing with our new atomic and molecular physics. And in the previous video of this series, we had discussed about the resonance lines. Uh, Now, and we had also obtained the Rydberg's constant value. But all that Rydberg's constant and all of that is going to change slightly uh, because we are now going to consider the finite mass of the nucleus. Now we already know that the nucleus has a finite mass, but it wasn't considered in the same way uh, whenever we made the calculations in Bohr's model. Even the energy and the other things, the angular momentum, all of that, the mass was considered as a whole for the entire atom. Now, the nucleus in that sense, when we were considering the mass, the nuclear in that sense was considered to be of infinite mass when compared to the mass of a mere electron. But if we consider the nuclear mass to be finite, then we will definitely have a center of mass. So we'll be having the correction for nuclear finite mass. Now the nuclear finite mass, well, this means that the nucleus will have a certain mass, let that mass be m, and the electron which is moving around the nucleus, that has a certain mass small m, and obviously the distance between the nucleus and the electron revolving around it, that is supposedly r. This entire length is r, and let there be a center of mass, the center of mass about which the entire system revolves because of the now finite mass consideration of the nucleus. So it will have an angular speed omega with which both the nucleus and the electron, this is the nucleus and the electron, they rotate about that center of mass. Let this distance from the electron be x for that of the center of mass, and therefore we are left with r minus x. There is a distance of the nucleus from the center of mass. Now, with the center of mass consideration, we have the moment of mass to be equal, because that's the way center of mass works. So this is the moment of mass of the electron about the point C, and the moment of mass for the nucleus about the point C. So we have the value x to be equal to m times of r divided by m plus m. Well, you can calculate that actually, because m multiplies with r and minus x. The minus mx goes to the other side, x goes common, and so we have this. Similarly, what we can find is that r minus x will therefore be equal to the mass of the electron multiplied with the distance separating the electron and the nucleus divided by the sum of the masses. So as you can see, this distance is relatively very small, because the mass of the electron when compared to this denominator over here, that is very less. So obviously r minus x will be very close to the nucleus. In our solar system, in fact, for the earth and the sun, the center of mass lies within the sun itself. So well, this is one of the considerations that we take, and from that what we have is the sum of the angular momenta. Now if we consider the sum of the angular momenta, what we get is the angular momentum is simply mr square omega, and instead of r square we can have for the electron we have its mass small m multiplied with the distance x which it has from the center of mass, because here the consideration is taken about the center of mass, the angular momenta, and that multiplied with the angular speed with which it revolves around the center of mass. And then we have the mass of the nucleus multiplied with the square of the distance, r minus x squared, times of omega. Now if we add these up together using these values that we have obtained over here, so m and x squared is simply mr divided by m plus m squared multiplied with omega, and then we have capital M r minus r, that taken mr divided by m plus m again squared multiplied with omega. Now from that what we get is the m and m squared, and then we have plus m times of small m squared divided by m plus m. I've written it the other way around, that squared again, and the r square and omega can be taken common. So from that what we get is the m and m, one of them can be taken common, and with that taken common we are left with m plus m divided by m plus m squared. So one of them gets cancelled out with this r square omega. So what we get here is simply m multiplied with small m, that is the mass of the nucleus multiplied with the mass of the electron, divided by the sum of the sum of the masses squared r square omega. Now this term that we have over here is what we symbolize as a mu r square omega, and mu is simply the reduced mass. Well, the reduction is completely dependent on the if I should say completely dependent on the heavier mass. The heavier the mass, capital M, the more inclined is the value to that value of capital M. Means let me give you an example over here. If m is 100, capital M is 100 and small m is just 1, so you have the mass capital M to be 100 times greater, or 100 times greater than the small m. So 100 times of 1 in the numerator divided by 100 plus 1, which is 101. So this is 100 divided by 101, which is nearly equal to 1. Well, that doesn't make any difference, so as to speak. So it completely depends on the capital M, that is the heavier mass, and in this case the heavier mass being that of the nucleus when compared to that of the electron. To some extent it is reduced. Obviously 100 divided by 101 is less than 1, so to some extent it is reduced, and so it is therefore a reduced mass. Well, the total angular momentum thus obtained is this, that is mu times of r squared times of omega, and that when applied to the Bohr's model, what we have is L is simply equal to mu r squared omega, which is equal to nh divided by 2 pi, and then again you have the expression for the energy of the nth state, and that also changes to mu z square e to the power 4. Remember, instead of mu there was the mass of the electron m, so mu z square e to the power 4, 8 epsilon naught squared h squared 1 by n squared. Now remember, mu, although it's a reduced mass, but it's much greater in value when compared to the mass taken earlier, that is small m, that is for the electron only. because the mass of the electron is much less when compared to the mass of the nucleus. So these changes, how would they actually affect the other types of calculations that we have made? Well, the correction of the nuclear mass has drastically, if not drastically, but to some extent, varied the value of the Rydberg's constant, which we are going to consider now. Now, in Rydberg's constant that we had obtained for the infinite mass consideration, we were writing it as simply R, but here we can denote it as R infinity, giving the infinite nuclear mass. For that, we didn't really consider the mass of the nucleus. What we had is the mass of the electron m multiplied with e to the power 4, that is the charge of the electron to the power 4, and uh, divided by 8 epsilon naught squared h cube, Planck's constant cube, and c being the speed of light. This was the value of Rydberg's constant. Now let us have that as r dash, and that is simply equal to the reduced mass instead of that proper mass that we were giving for the electron. Now we have a variation in Rydberg's constant. This is a varied Rydberg's constant. And so r dash here is simply mu e to the power 4 divided by 8 epsilon naught squared h cube c. And if we write it explicitly, then what we get is m times of m divided by, well, we can place the m plus m on the other side, 8 epsilon naught squared h cube c, and the m plus m that was over there, I write it over here. And if I take the capital M from this and I divide it over here, there shouldn't be any problem with that. And what I get is m e to the power 4 8 epsilon naught squared h cube c, and this one m by m goes to 1, and this is simply m divided by m. Now this value that we have over here, if you see, it's exactly this one. So this is R infinity, considering the infinite mass of the nucleus compared to the mass of the electron, and then we have that divided by small m by capital M, mass of the electron by mass of the nucleus. And so here R dash, because we know the value of R infinity, so we have R dash to be equal to 109,677 centimeter inverse, which is about 1 by 2000 times less than the R infinity value. Well, this amount that you see over here, that may seem very negligible, but obviously that puts some impact on the result thus obtained. Now if you observe the variation, if we are to observe the variation of the Rydberg's constant thus obtained with this correction, finite mass correction, then we certainly have a view of what it does. Now the values of Rydberg's constant, they keep on varying with the mass number, right? So this is the mass number, and this is the value of Rydberg's constant taken as R dash, which varies. And let me just put a few values over here: 700, then 720, 740, this one is for hydrogen, this is for another isotope of hydrogen that we'll be discussing shortly. This is for probably for helium, then for lithium, oxygen, likewise. And what it does, it moves like this, the value changes, asymptotic, doesn't go above that. This is the nature of the variation that we obtained. Okay, that's on an experimental basis. So the mass number obviously here, as you can see, 1, 2, then for helium it is 4, and then for lithium it is 7, for oxygen it is 16. So it goes on varying. R infinity is just below this. This is for R infinity, which is just below that 109,740 mark, and thus we have the variation of the mass number uh, likewise. Now, well, from Bohr's model, we had obtained we can obtain these values by just putting them over for Bohr's model, the value of Rydberg's constant that we had obtained, and further on investigating, we can also obtain the Faraday constant just by using these values that we have obtained. We can just obtain the Faraday's constant, which is the ratio of electron by charge of the electron by mass of the electron, and that goes to that becomes equal to 1.77 times of 10 to the power 11. There are a whole lot of calculations involved, but we are mainly concerned with the results. But obviously the calculations involve um, the Rydberg's constant, that for the Rydberg's constant. Now, with all of these things, there was another thing which appeared because of this finite mass correction that we had, and this was probably observed by a person named Urey in 1932. Well, when he photographed hydrogen spectrum by means of a large concave grating apparatus, he observed each hydrogen line was accompanied by a very faint line slightly on the shorter wavelength side, and that shorter wavelength side that he obtained, he measured the wavelength difference, and he attributed the faint line to some heavier isotope of hydrogen, and that is why it was termed as heavy hydrogen, which is popularly given the name that we know today is deuterium. And that is exactly this thing that we just wrote over there, plotted in that graph, the isotope of hydrogen. And it's not that abundant. The availability is usually 1 in 5,000 parts for a given hydrogen sample. Okay, so that is the heavier isotope of hydrogen, and with that this has been obtained by the finite mass correction. That was, it can be calculated though. What we can do is calculate for that deuterium. The Rydberg's constant is simply R infinity divided by 1 plus m divided by the mass of the nucleus in case of deuterium, and that is equal to simply 109,737. remember, it's below 740, and this divided by 1 plus 1 by, now the mass of hydrogen nucleus is 1836 times the mass of the electron, because it is just a proton, so the proton mass of the proton is 1836 times that of the electron. So, and this is 2 here stands for that deuterium that we just are considering over here, and that is giving us 109707 centimeter inverse. This is the value of Rydberg's constant, which is associated with heavy hydrogen and has double the mass. That is why we have the factor 2 over here. And one of the things that we came across because of this finite mass consideration, had this formula not been taken into account, then we wouldn't have achieved such a result. See over here, this 1 plus m by m, that factor is pretty relevant in this case. So the H alpha line of deuterium is about 6561 angstrom, right? While that of hydrogen is simply 6563 angstrom, right? This is for hydrogen, this is for deuterium. Okay, it's a very small difference, but it is quite sufficient for the identification of deuterium, right? So this general nature of two spectra is um, however exactly the same, because the atoms are that of hydrogen and deuterium. They have the same electron structure, which is about moving about them. Up next, in the next video, we'll be comparing the hydrogen and helium spectra, and thereafter we'll be moving over to the Wilson-Sommerfeld quantization rule, which will be of a lot of help for going into further detail of this topic that we have started. Till then, thank you for watching.